Welcome to this tutorial where I'm going to talk more in detail about linear regression. Now, let's go through this by an example. Let's assume you're a quite big international company and we would like to predict our sales volume. We would like to use publicly accessible information like world GDP growth in percentage to make a prediction about what our sales is going to be like. So we assembled some data for several years and this will serve as our data set. Our basic idea is that there will be a linear relationship between those two. As you can see from the graph, you see if you plot those values, you can see that the relationship is actually nicely linear and you're probably gonna easily fit a nice regression line through it to make predictions. More formally, our model, sales volume being our dependent or y variable, and GDP growth being our predictor or independent variable, the x variable, would look like this. So your variable of interest is a function of x plus some error. So in this example, our sales are a function of GDP growth plus error. We always have the error because no model predicts perfectly, right? More formally, our stochastic model looks like this. So this is the regression equation. This is nothing else than a specific predicted, estimated y value is your intercept. Beta 0 is the intercept of your regression line. Beta 1 is the slope, which is multiplied by your x value, so your predictor value, and then some error. So you can calculate your predicted sales volume if you have intercept, slope, and some, in this case, GDP value. Now, all statistical software programs let you calculate the regression easily. I did this here with Excel, but this is just for illustrative purposes because it gives you also a nice plot. So the blue data points are the observed sales volume, and the orange squares are the predicted values using a regression. So you can see that this makes a straight line if you connect those orange squares. But still, you will have some error, right? As pointed out before, you can see that these actual values differ from the predicted ones, right? And usually I would say when I talk about this, well, the software finds the best fitting line for you, which minimizes the error. Now let's have a look how this is actually done. So this is done by using ordinary least squares. Ordinary least squares estimator helps you in finding the regression line with the least error. Of course, you will always have some error in your model. As you can see here, this is the fitted line through the data, and you still have discrepancies between your predicted value depending on your regression equation and the actual value. So those errors remain, but you have the best fitting regression line. So the OLS helps you in finding this line. It minimizes the error you have in your model. All other lines, all other regression equations would have a higher error sum, right? So to explain a bit more in detail, so what you have is you want to minimize all those discrepancies you have between observed and predicted values, and you have to square them so that they don't cancel out, and you have a sum of errors, so you want to minimize those to get the best fitting regression line. Now, this is just the same as that. If you remember the regression equation, you remember there was an error and a predicted value and so on. So this is just the same thing. Here you have an observed score, right? Observed sales volume. And then you deduct your predicted value, which is just the intercept of the regression line, and the slope times the plugged in x value, right? So if you deduct your prediction from the actual score, the only thing that remains is the error. So it's the same thing, don't forget to square it. And you want to find the minimum. So it's an optimization problem. Now, to actually go through the analytic steps, this is a rather tedious process, and you would start with getting the partial derivative of beta 0 and beta 1 and setting them to 0 because it's a minimization issue, and so on and so forth, and you have transformation and do solve in the end for beta 0 and beta 1. It's actually sufficient if you know this formula of how you get the beta 1 and beta 0. Actually, beta 1 can be further simplified by using means, but we will just stick to this formula for the slope beta 1 and to this for beta 0. And I'm going to talk in more detail about the formulas in the example. We will just go through that. What is here to say, except that if you have beta 1 and beta 0, you have your regression equation defined, and that's all you need. Now, for our example, this is the data set we already know. This is just replicated here. And then we have the product of x and y so you do this for each observation. And this is x squared. And then here in this row, we have the sums. This is just done to prepare for the formula. This is more of a mechanical exercise, but I will still talk you through it. So, and we have, of course, the mean of x and the mean of y calculated as well. So first we have to get the slope because it's necessary for getting the intercept as well. So we will start here. So k denotes just all the elements we have, like all the observations. So those are 10 observations from 10 years. And then, well, you have just summed products. And then you subtract sums of x and y. And then below again, your number of elements. And then you have the squared x and then sum it. So just be careful here that you square first, right? And then you sum, or you sum and then square it. So here I just put this with the numbers. I didn't bother to write the decimals, but I think you can still find the corresponding values, right? So you can just have a look at this if you're having trouble identifying some terms, some corresponding terms. Now here and then the intercept, this is a much more appealing formula. You just take the mean of y minus beta 1 times mean of x. So those are the calculated values and they match those I got with the analysis tool. So that's basically it. And you can be sure that you found the right regression line because you solved it analytically as we discussed in short before. But if you would like say you would calculate the sum of squares residual, we will talk about the sum of squares in a bit. But this is just your error. This is the sum of squares for the actual fitted regression line you just saw before. So that's 146. And here I just put some random variable which is close to our calculated value, so plus minus 2 for intercept and slope, right? And then I would also get a residual value. So let's just see how this changes, right? So this is actually already quite close to what we calculated, but as you can see, any other value will give us a larger sum of squares. So residual. So the error is always higher if you compare it with the actual value we calculated. It could only be exactly the same if we got by chance the right intercept and slope value. So it's just to show that the analytical solution is obviously correct and it minimizes the error you have in your regression model. Although I enjoy seeing cascading numbers, we have to get back on track. And now the final step, it's not the complete final step, but for the overall model, you will look at the sum of squares and the F value. So to see if your model is actually a good model. So let's start with the sum of squares. First, you have to calculate the total sum of squares. So this is done by subtracting the mean from each observation and squaring it. Then you sum it up. This is your sum of squares total. So this is the variance you can maximally explain, the total variance there is, okay? And after you have done this, you want to see how much of this variance your model explains, right? So you will take your regression equation that we discussed before, and we calculated. So we have beta 0, beta 1, and you will just put in the values, right? And then plug in the corresponding x here, right? And then again, for the total sum of squares, your comparison was the mean, because it's the base model compare it to. But here, your prediction, which you established by using the regression line, will be the comparison between the observed value and your predicted value. And you see that's the error between those two squared. Don't forget to square it. It's the sum of squares. So here we compared observed value with mean and then squared it. And here it's observed value and your predicted value. So when you get this, those are your residual sum of squares. So this is the error you still have in your model, despite using the regression. So that's this. This is the error you still have in your model. Now, if you want to know the sum of squares of your model, you simply deduct the residual from the total, because then you will get what your model, your regression, actually explains. After having calculated those sum of squares, you can calculate your R square, your variance explained. Of course, you will use the sum of squares of your model divided by the sum of squares total. It's just a ratio between what your model explains to what is there in total to explain. So 93% of the variance is explained by the model, which is extremely high. But now you would like to know, okay, this already looks good, but you would like to know, is my regression model a better predictor than just taking the mean? So as a next step, what you will need is the mean sum of squares. You get those by dividing the sum of squares by the corresponding degrees of freedom. So your degrees of freedom, the total, are your observations, your elements, so 10, we have observations from 10 years, minus 1. Then we have the degrees of freedom in your model. We have one predictor, which is GDP growth, right? So degrees of freedom is just one. It's just one parameter, right? And well, the residual is then your total number of observations, which is 10, minus 1. But you have to deduct another degree of freedom because of your model. So it's just total minus the degrees of freedom you have used up in your model. So we have 8 here. So you divide the sum of squares by the degrees of freedom, and then you will again construct the ratio, so which is then already the F value. So you have the mean sum of squares of your model divided by the residual. So you're basically looking at the ratio which compares of how much you explain in comparison to what you don't explain, what is still the error, the residual. Obviously, the higher the F value, the better the model, or in the sense that the more likely it is that your regression model is better than the mean as a model. So it predicts better than the mean if it's significant. So you would then get an F value, which you again can compare to a critical value table of the F distribution with a set alpha level, let's say 0.05. But what you should pay attention to is that here you need 2 degrees of freedom. So you have degrees of freedom in the numerator, which are those of the model, and also those in the denominator, the residual. And those 2 you need to look it up. And if our F value exceeds the critical value in the table, it is significant at the given alpha level. But you can also ask your statistical software program to calculate the exact p-value, like for example here, so you can see this is highly significant. So we see that this model is actually good, and it's a better predictor than the mean as a model. And obviously you can then continue to do t-tests for your coefficients, but here we established first that the overall model is significant. Good luck in your statistical endeavors. Thanks for watching. See you next time.